All right, so the last thing we just talked about, how to use those rules to make Lewis structures. Those are those things with those lines and the dots and figure out who's attached to who and where the electrons are. Now we're going to start to make sense of it. Why are we doing these Lewis structures? Well, it turns out these Lewis structures, not only do they predict what molecules actually look like, hey, that oxygen is connected to those two hydrogens with those two lone pairs on it. They also predict the shape of those molecules and how those molecules interact with molecules that are nearby. So the next thing we're going to do is we're going to look at shape. How does our Lewis structure help predict our shape? And we're going to use a theory that's called valence shell electron pair repulsion theory. Now, that sounds really fancy, like, ooh, whatever. And people call it VSEPR. They really should call it VSEPR, but it's called VSEPR. But what does it mean? Valence shell. Those are those outermost electrons. You know what those are. Electron pair. Well, electrons generally come in pairs, and we've been drawing those lines to represent electrons pairs. So valence shell electron pair repulsion theory. I'm just going to move my camera here a little bit so I'm more in the middle. Okay. Well, repulsion. What do electrons do? One electron repels the electron next to it. They don't want to be near each other. They try to go far away from each other. And it turns out just using that, you can really predict the shape of molecules. So it's not just a bunch of dots and lines like it looks like. We can actually do it. Now, this is an older slide, so you can tell it's at least 5 or 6 or 7 or 8 or whatever many years old, because it's talking about Obama. And I can't remember her name at the moment. Oh, not coming to my brain. But anyway, they didn't like each other, right? They're always going to go as far apart from each other as they physically possibly can. Same thing for electrons. They don't want to be near each other. They have to be in order to make these molecules. There's good reason to make the molecules, but if they're going to have to make a molecule, they don't want to be close to each other. They want to be far apart from each other. So that's what we're going to do in our theory. Now, there's a few different ways we can talk about this, right? If we have a good old central atom right here, ba-ding, there's our central atom, and we start attaching things to him, there's just one thing attached. Where's the next thing going to go if you're attaching it and wants to be as far apart as possible, right? Is it going to attach up top there with these guys at 90 degrees? I don't think so, because there's a way for it to attach where it's further away, and that is if he attaches straight on the other side. And now we have 180 degrees. Because right on this atom over here, there's electrons. On this atom over here, there's electrons, and they don't want to be near each other. They want to be really far apart from each other. And so what do we end up with? We end up with molecules with one central atom, that's our blue, and two atoms hanging off of it always end up as a linear shape. Right? This looks like a line, and we call it linear. So let's delve into some more things. Okay, so this is what we just showed. If we have two friends, what's it going to do? It's not going to be 90 degrees. It's not even going to be 120 degrees over here like this one. It's going to be as far apart as possible, which we called linear. Makes somewhat sense. All right? How about if we have three things? If you have a central atom, that blue circle there, and there's three things attached to it, where are they going to go? Well, you might just put them like we do with the Lewis structure, right? You just kind of draw everybody at 90-degree angles. But then you have this guy at 90 degrees, and this guy at 180 degrees, and there's a little bit of jealousy. Well, how come he has to be really close to him, but he can be really far away from other people? So let's separate them out a little bit more, right? Let's start to spread out this guy. And maybe now we have 100 degrees and 100 degrees, but that still leaves 160 degrees, and those guys are still further away. But what happens when we make it all equal? 120 degrees, 120 degrees, and 120 degrees. Well, then everybody's as far apart from each other as they physically can be, and that's actually where the molecule is happiest. The molecule is happiest when everybody is repelling each other, right? Because there's electrons on the outside of this purple atom, there's electrons on the outside of this purple atom, and electrons on the outside of that purple atom. They're far apart now. Now, it turns out this shape has a name. It's called trigonal planar. Right? And remember, planar just means flat, like a plane. If you make 3 points, you have a plane in math. Planar just means flat. So it turns out this molecule is perfectly flat. Now, in class, I often do this with balloons, but it turns out it's going to be really hard to do balloons in front of this camera that's really close to me. So I also have these little model kits. Okay, now this little model kit, what we're going to do is we're going to pay most attention to the atoms in this molecule kit. So what we have here is actually something we drew in our last video. This molecule, CH2O. There's our hydrogen, there's a hydrogen, carbon in the middle, oxygen on top with this double bond. Now in this model kit, the double bonds kind of tweak out like that, but we're going to pay attention to where the atoms are, not where the bonds are. And what do you see? Oh, look, everybody is separated from each other by about the same amount in this model kit. And so it does that all by itself, which is really cool. So what else can we look at? Well, if you look at from the side here, and it's a little bit hard to see in there, but if you look at the side, all 4 of these atoms are all in the same plane. It's flat like a piece of paper. Again, if you don't pay attention to these bonds here, flat like a piece of paper. And so we get trigonal, 3 things on the outside, flat as a paper, planar. And that's what the molecule does all by itself. Well, let's get even bigger, right? We drew SiH4 in the last one, and we said it looked like this. We also drew CH4, and it looked very similar. But what does it actually look like? And you're like, well, maybe it's 90 degrees. Everybody's just 90 degrees from each other. But it turns out you're limiting yourself there. You're saying, well, everything has to be flat. But it turns out, amazingly enough, that's not what it does. What it does is instead of being flat, it's actually 3-dimensional. And here's kind of a 3-dimensional representation of it. And here is one I made, which is CH4, carbon in the middle, 4 hydrogens on the outside. And you can see pretty darn well that this thing is not flat. In fact, if I put it on my hand there, you can see that it sits on my hand and the carbon's off the ground, even though those other hydrogens are on the ground. This is a very 3-dimensional structure. Now, when you draw this structure, what you find is that all of your angles are about 109 degrees. So it's better than 90, right? If it was flat, it was 90. But when you go into 3 dimensions, you can get everybody far apart, which is 190 degrees. Now, this kind of looks a little like a pyramid, right? I've got that little pyramid on the bottom, and there's a face here, and a face here. And so there's actually 4 faces to this guy. And so we use the word tetra, which means 4, and hedral, which talks about faces. Now, you don't really have to worry why tetrahedral is called tetrahedral. It just is, but that's why. And that's what we call the shape when there's a central atom with 4 things attached to it. So our 3 shapes so far: linear, trigonal planar, tetrahedral. Well, is that it? Are we done? Well, it turns out something funny happens in other cases. What's the case that happens where instead of an atom here, there's a lone pair here? Now remember, the theory is called valence shell electron pair repulsion theory. So if there's a lone pair here, a lone pair. By the way, a lone pair is a pair of electrons that is not participating in bonding. I don't know if I defined that yet. Well, it's a pair of electrons. Isn't it going to repel other things? And the answer is absolutely. In fact, it does a really good job repelling things because it's not busy being part of an atom. Well, let me take that back. It's still part of an atom. But right, it's not busy doing other things. So it's really good at repelling other things. All right, so what does that look like? Well, lone pairs. They're kind of there, but they're kind of not. So what we have here, let's see, we have this guy. We looked at this guy before. But what would happen in this case if we just couldn't see this oxygen atom? He was still there. What do you mean we can't see it, Professor Coleman? It's right there. You can see it. Okay. But remember, if we have just electrons here, electrons are ridiculously tiny. If you stand back a few feet, you're not going to be able to see them. Right? So when we have a pair of electrons up here instead of an atom, you really can't see it because it's so small. So what I have here is another molecule. Now all of these blue ones are oxygen, so this is O3. There's 3 oxygens there. And this is actually ozone. And ozone, now there should be some lone pairs out in the sky, but I didn't have the right atoms for that. But ozone looks something like this. And oxygen is a central atom, 2 oxygens on the other side, and a lone pair up there. What do you notice about the shape? Right? Even though there's only 2 things attached, it is definitely not linear. Right? It's got this kind of bent shape. But if you stuck an atom up there, it would look a lot like trigonal planar, what you see over here on the left. But when you can't see one of those atoms, right? This guy's tiny. It's there. There's a pair of electrons. Those electrons are repelling these electrons, which is why they're bending away from him. But if you can't see it, maybe we shouldn't talk about as if we can see it. And so if one atom is invisible, you see something that looks a little more like this. I can put that at that angle. Or I guess it's really hard when things are backwards at that angle for you. Okay. And what do we call this? Well, we call it bent. if we just look at the atoms, that looks like something that's bent to me. It no longer looks like a trigonal planar. So it turns out now we have two things that we can talk about. We can talk about the geometry, which people also call the electron arrangement, the electron geometry, and we can call the shape. And geometry is when we consider atoms and lone pairs. And so for this ozone, if we consider atoms and lone pairs, we've got one atom, two atoms, and one lone pair. 2 plus 1 is 3, and we have trigonal planar. In fact, for this class, the only three geometries you're ever going to get, linear, trigonal planar, tetrahedral. Those are the only three geometries. Shape is when you say, OK, now I've got this geometry, but what if I can't see one of them? What do we see? Just the atoms. It looks bent. Okay? So geometry takes into account atoms and lone pairs. Shape comes after you consider geometry. You have to do geometry first. But then if you can't see one of them, what does it look like? And in this case, it looks bent. OK, one more. What about our tetrahedron? What is our tetrahedron going to do? Well, our tetrahedron requires that 4 things are attached. Now, what I forgot to make for myself when I did this is I forgot to make one that looked like what I'm about to talk about. So I'm going to pretend. I'm going to take this guy here, CH4, and pretend that I could just take this guy off. Pretend that I can just take that guy off and put a lone pair there. I can't do it, but I wasn't prepared. Now, I had something that was tetrahedral, but if you can't see this guy anymore, is it still tetrahedral? One that we did that looks like this is PCl3. When we drew it, it was P with 3 chlorines. They all had some lone pairs around them. But the phosphorus had a lone pair as well. So we had 3 atoms, 1, 2, 3 chlorine atoms, a phosphorus with a lone pair on top. If you consider all of them, that's 4 things, and it looks like tetrahedra. But if you can't see that top one, and right now we can't see it because it's not there, it doesn't look like a tetrahedron anymore, right? It looks like a little pyramid, doesn't it? And what we do is we actually call that a trigonal, right? There's 3 things, pyramid. Different than trigonal planar. Trigonal planar was when it was flat. This guy's not flat. He sticks up a little. Okay, he sticks up off my hand. That's what we call a trigonal pyramid. What if there's 2 lone pairs? Like, oh, when would there ever be 2 lone pairs? Well, remember, what did water look like? Water looked like an oxygen with 2 lone pairs and 2 hydrogens. So in this one, I'm using green for oxygen. Oxygen, 2 hydrogens, 2 lone pairs. All right, so what do we have? Right? If we consider all of them 2 atoms plus 2 lone pairs, 2 plus 2 is 4, then it would look like a tetrahedron. If there were things sticking up here, it would look like a tetrahedron. But without that, what does it look like? Again, it looks kind of bent. Now the angle is a little different. This angle is 109 because it comes from a tetrahedron. In the last slide, the angle is 120 because it came from trigonal planar. But they both still look bent. So now we have the ability to not only look at the arrangement of things, where the atoms are, but we can also talk about their shape. 3 main geometries: linear, trigonal planar, tetrahedral. Then, once you figure out those, if there's no lone pairs, if you draw a structure with no lone pairs, like my CH4, and by lone pairs, I mean lone pairs on our central atom, right? There's no lone pairs on that carbon. Geometry and shape are the same. So I've got tetrahedral geometry, tetrahedral shape. As soon as you start to add lone pairs, 1 or more, geometry and shape are different. And you have to look, what do I have? Right? I no longer have a tetrahedron, I have a trigonal pyramid. I no longer have a tetrahedron, I have bent. I no longer have trigonal planar, I have bent. Now there's lots of other structures, but we're not going to go over them in this class. So we're going to stick with up to 4 things, and that's as high as we're going to go. So hopefully you have a sense now of how to use VSEPR theory, valence shell electron pair repulsion theory, in order to predict shape.